Hi everyone, my name is Haight, and the goal of this video series is to essentially give an introduction, maybe more than an introduction, to algebraic number theory. So this first video is just kind of like an overview of what this series of videos is going to look like. So this is the introduction. Okay. This first video will be pretty short. It'll just be an overview of what the goal of this project hopes to accomplish. So first, what do I want to say about algebraic number theory? Okay. So for the level that we're going to be going, there are a few prereqs that I would recommend you you have a grasp of before watching these videos. So the prereqs. First, you should probably have a little bit of background in elementary number theory. So like a 1/4 class talking about like the Euclidean algorithm, modular arithmetic, stuff like this will almost certainly be useful and kind of presumptive knowledge for the content of this course. And the second, which is kind of a more substantial prerequisite, you should be familiar with, you should essentially have like a year-long course in algebra under your belt. So group theory, ring theory, modules, okay, field theory, and you should at least have some idea of the basic ideas of Galois theory as well. Okay, so your typical like year-long like 400 level, I guess, course in algebra, that will probably be perfectly fine for this class. For the first few lectures are going to be about mostly the commutative algebra, building the necessary commutative algebra to talk about the number theory I'm interested in. So if you're a little rusty in some of these topics, maybe I wouldn't worry too much. So these are the prerequisites for this series. What are the goals? The goals here are going to be kind of vague. One of the goals of basic algebraic number theory is I want to understand finite extensions, okay, of Q and their rings of integers. Okay, so if you don't know what a ring of integers, that's totally fine. We'll get there. But the simplest example is Q has ring of integers Z. So if you're interested in numbers, you're probably interested in Z. And these number fields are kind of a natural generalization. The rings of integers. Okay. Okay. Kind of like the next step that you would take after something like this is to try to understand the basically class field theory, abelian class field theory. So prepare for an understanding of class field theory. Class field theory, and really like if you intend to do like any like graduate level work in number theory, this algebraic number theory is, unless you are like really analytic, algebraic number theory is going to be an absolute necessity. So just developing this language is super important if you want to do modern number theory at all. And modern number theory as a whole. Okay. So this video series is going to follow a text which is freely available. It's algebraic number theory, by J.S. Milne, and the goal is to follow this probably like very closely. So basically I want to work through Milne's notes and fill in the details where maybe Milne is a little vague. Okay. And this is freely available, and the link will be in the description. Okay. And so here's the text. What are going to be the major topics that I plan to cover? Okay. So the first major topic is maybe a little boring but necessary. These commutative algebra prereqs. So rings of integers are commutative rings. As you might expect, it can be useful to study commutative rings in general before we consider the specific case of rings of integers and these number fields. Okay, commutative algebra prereqs. Okay. The second major topic is going to be rings of integers. So, as you might expect, I keep saying this word rings of integers. We might want to introduce it pretty early on in our study. Okay. 3. I want to talk about basically Dedekind domains, which it turns out that rings of integers are Dedekind domains. Factorization of ideals. And ramification. Okay, so this basically, it turns out that it's important to study how it's important to study ideals in these rings of integers, and in particular how if I take a prime over Q, or a rational prime, or a regular prime number that you might know, how that ideal breaks up into different prime ideals when I look at extensions of Q. Okay, so if that doesn't make any sense, again, we'll get there. Okay, the fourth thing, I want to talk about the class group of a number field. This is useful. I guess the most apparent way that this is useful is that it tells you in some sense how far away your ring of integers are from being a unique factorization domain, but it also captures important information. Just in general, it captures important information about your rings of integers. Class group of a number field. Okay. 5. An important result that I want to prove is Dirichlet's unit theorem. Okay. This tells you about the units in your rings of integers, basically like what kind of ring that is, how big it is in some sense, stuff like this. I want to do once we've developed all these pieces, I want to do an example of the cyclotomic extensions, and what can we say in this case. In particular, we'll prove a special case of Fermat's last theorem. Cyclotomic extensions. Okay. 7. The last topic is going to be about, I guess, slightly more analytic or topological in nature, and these are going to be about absolute values. local fields. Okay. And their relation to number fields. Okay. Already I realize I've started using this word number field, and you probably don't know what it is. A number field, my note is NB here. A number field is just a finite extension of Q. Okay, so these are the goals for this video series, and we'll start with one in the next video. So have a good day.